The other issue I have is I don't have a microphone, so hopefully the sound is okay on this. All right, so on Wednesday, I'm going to finish it a little bit early, my lecture, and I want to go outside and do a couple of demos. It'll be with liquid nitrogen, so just for fun because it's the end of the course. Okay, so we'll do that. So hopefully you can stay a little bit after 9:30 for the demos because it might take a little while. Okay, so we'll have some fun, I guess. So what I want to do today, like I said, I'm not going to go the whole class period. I want to talk about the material in chapter 13. I just want to start the material. And so these are the topics we're going to cover in the chapter. And I literally spend almost the whole lecture on gravitational fields of continuous mass distributions. And this is where you're going to be learning how to set up the integral. And one of the things I said, or I will say, is you'll have a problem on the exam. I'll have more to say when we get to that lecture. You've already seen me introduce the law of gravitation. It looks like this. Right, I haven't written it as a vector. Law of gravitation basically describes the gravitational force of attraction between two objects. Two objects are attracted to each other just because they have mass. It has nothing to do with charges or anything. There's a separate force for that you will learn in Physics 210. And the expression looks like this. The magnitude of this force, we'll write it like this. Now let me draw a picture showing you two objects. Here's object 1 of mass m1. Here's object 2 of mass m2. The force of attraction is along the line joining them. Okay, the force of attraction is along the line joining them. So I want to talk about different parts of this equation. Well, in this equation, at least for the magnitude, m1 and m2 are the two masses. G is the gravitational constant. So G, and we wrote this down earlier this semester, is 6.67 times 10 to the 11th Newton meters squared per kilogram squared. And it's a fairly small number. You'll learn in the next course the analog to this for the electric force. It's about 20 orders of magnitude larger. Okay. All right. So we talked about these two terms. Let's look at the denominator. The denominator is the magnitude of the vector that points from the source of the force. So if we're going to focus on object 1, if we're going to focus on the force on 2 due to 1, I'm sorry, the force on 1 due to 2, and this is the source that's producing the force on 1, that's the vector. So that's the magnitude of the vector that's directed from the source to m1. Does that make sense? I mean, you can think of it as just the distance between the two objects, but I'm being a little bit more precise. That r is a distance, it's not a radius. Okay, it's the center-to-center distance between the two objects. Okay?
From the centers of mass, right?
From the centers of mass. Okay. And we're going to say more about this equation when it comes to, we're going to look at the symmetry of the object. We're going to assume that these objects can be treated as point particles. And we'll find that you can treat spheres as point particles. If you have something that's not spherical, the problem's a little more complicated. We have to break up the object into small parts.
So can we say that the force of the mass of 1 on 2 is going to be the same as the force of 2 on 1?
That's a good thing to bring up. They have to be the same, right?
Because the same distance. Yeah.
The same distance, right? The force on this object is going to be the same as the force on this object because it's the same distance. You have the same two masses. What else are we going to have to, does this have to not violate? Which of Newton's laws? The third law, right?
Yeah.
We can't, we shouldn't violate the third law. What does Newton's third law say?
Every reaction is an equal and opposite reaction.
Yeah, so we got to obey that. And this does obey that, right? Now I got to be careful. This works as long as the distance between the two objects is not that great. Imagine if these two objects were really far apart and this moved a little bit. Let's say there was some sort of perturbation that made this move, so the distance slightly moved. Or let's say this thing just exploded, like a planet exploding. Is this planet going to feel the effect instantaneously?
Yeah.
That means that the time rate of change of momentum of this one and the time rate of change of momentum of the other object are not going to be equal, right? Those are forces. The forces won't be equal and opposite. And the reason why, because it takes time for the information of the explosion from this object to reach that object. So these two are not going to be the same. So Newton's third law doesn't really work when objects are really far apart. There's something that will take care of that. We'll talk about it later today. Okay, so yeah, you brought up a good point that they do have to be equal and opposite. Their accelerations don't have to be the same because the accelerations depend on the masses of the two objects, true? Because to find acceleration, we have to apply Newton's second law. And we see that when we talk about the gravitational force of attraction, let's say between this marker and the ground, and the Earth. If I drop this, obviously this falls at a rate of 9.8 meters per second squared, but the Earth is moving upward too. But the mass of the Earth is so much greater that the upward acceleration of the Earth is very small. You can't even measure it. Okay, so although the forces are going to be equal and opposite here, the accelerations are going to be different because the masses are different in general. Does that make sense? Okay. So good. You brought up a good point regarding that, and I need to find my eraser.
Was there audio in the OBS recording? Because I didn't see the audio go.
Am I recording?
You're recording, but I think there might not be audio.
Well, I tested it. It was
Sure?
responding. It's either using the camera or my computer. I forgot to bring my microphone. I have an external microphone. I forgot to bring it. So hopefully it worked, but it looked like it was working in the program. Okay. Let's talk about the vector. Writing it in vector form. This is how we write it in vector form. It's minus this quantity times the unit vector r12. The unit vector r12 is the unit vector that starts at the source and ends up at the point which you're determining the force, or the object from which you're determining the force. It goes from source to point. That's what r12 is. It's always written that way. Okay, so even though this vector points this way, which way is this thing going to want to move? Downward. That's why we have the minus sign there. Does that make sense? So it's always written like this. Questions on that?
Yeah.
Just to clarify, so our R hat there is like a new axis that is simply gonna be the magnitude of the vector, right, or following along that vector.
Following along that vector, it's
Okay.
the direct, yeah, you can think of it as like an axis, right? I mean, R12, the unit vector R12 is the vector R12 divided by its magnitude. Right? That's what a unit vector is. If you don't like, like I said, I'm being very precise when I'm saying this, which becomes important when you take take these courses at the next level. But you can just think of this as the distance between the two objects, at least for now, if you want to. If you don't like this, at least you can think of it as the distance between the two objects. But I'm writing it this way because when you start doing some other work with these equations later on, knowing this precise definition for R12 is important. Okay, do you have any other questions? It's a vector, right? Remember that this is a vector, and it behaves the same way as the vectors we covered in chapter 5. It's no different. Sometimes when we cover a different topic, even when we do magnetic fields, the students treat vectors differently. Vectors have the same behavior no matter what. It doesn't care what kind of physical quantity is behind it. You treat the vectors the same. If you're going to add them up, you got to break them up into components, sum the components, and then use the Pythagorean theorem to find the magnitude. Okay? So that's something you have to remember. Students tend to forget that. Okay. So let's do an example. I want to know what is the force on the mass at the origin in that figure due to the other two masses. Okay. So let me draw a picture. And I am not going to use this form of the equation. I'm not going to do this. I have to rewrite it because I just erased it. I'm not going to use this form of the equation. And of course, this form of the equation allows you to determine the direction. But there's another way for me to determine the direction of the forces. What would be the other way? It's more physical than doing this. What am I going to do what is the first thing I do when I solve this problem?
Look at it.
Besides looking at it.
Draw a picture.
The picture's there.
Little axis, free body diagram.
Free body diagram. If a problem involves a force, the first thing that should pop in your head is free body diagram. Okay? That's always got to be the case. So here's the three masses. Let me write a distance. I can't use too many bright colors when I'm videotaping. I should say recording. We're not using tape anymore. So I want to draw the forces acting on this object. What is the direction of the force on this object due to the big one?
Positive X.
Okay. We'll call that F1. What is the direction of the force on this object due to that one?
Positive Y.
We'll call it F2. So F total and this is going to be easy because how many components is the force between these two going to have?
Two.
Between these two?
Oh, one.
One, okay. And in between these two?
One.
So one's in the x direction, one's in the y direction, so that's gonna be easy, right?
What about between the M mass and the 4M mass?
Oh, between these two?
Yeah.
That's a good question. There is a force between those two, right? But what am I asking? I'm asking for the force on this one, right? I'm not asking for the force on this one, and I'm not asking for the force on that one. Only this one. It's true that they are exerting a force on each other, but I want to know the force on this object. Okay? So you only draw the forces, a free body diagram on the object in question. So we're looking at this one. Okay? Because the force on these two is not going to affect the force on this object. Independent. All right, so what is the magnitude of F1? We use G times the product of the two masses. Okay? And what does this come out to be?
G, 8M.
And this simplifies, doesn't it?
86 times.
Okay. What about between these two? The product of these two? And then I sum the forces, right? I can write this in unit vector notation. What's the direction of the force?
I have a question. So for the first one, F1, the rate or the distance between them is 2r,
Yeah.
and you plug 2r squared is equal to 4r squared.
Yes. Times 2 is 4, right?
Oh, and then the r becomes squared as well.
Right. And I squared the whole thing.
Okay.
What direction is what's the direction of the force? You got to know that right away. I want an angle.
45, right?
45. Okay, good. Why is it 45?
Inverse tan.
Those two are equal.
Yeah, because the x and y components are equal. Okay? Question?
We're calculating force 2? Or is it still force?
This is the total force, right? It's that component plus that component gives you this force, right?
Yeah.
We're summing forces just like we did in chapter 5.
And I missed it. What about, are the forces on the 2m and 4m equal to 2m and 1m? Because the relative masses are the same.
We have each component is equal to each other.
No, I'm talking about between the two masses. 2m and 4m, the 0, this, and the other two. Are the forces equal?
I'm sorry, I'm not understanding what you're saying.
Okay, I see your question. They are equal.
The force between these two objects is this.
And what about the other two objects?
What's wrong?
Nothing.
Okay. How do I find the magnitude? Pythagorean theorem, and because they're equal, I should be able to write this down, right?
Yeah, yeah.
45, 45, 90 triangle, right? Okay. So I should be able to write down. You can use the Pythagorean theorem and prove it to yourself that you get that. Other questions?
How is it 86 times squared? That's G. It's G.
That's a G.
Oh, my bad.
Sorry, my G's are bad, okay?
Oh, it's G. Oh, that's G.
You're focusing on this one.
Yeah, I was like, how did that simple play down to
26.
Are we okay? Okay. So I want to say a couple things about the gravitational force. Actually, I want to compare the gravitational force equation to Newton's second law. Can you erase this? Let me write the two equations down. And I'm just going to focus on the magnitudes. So I'll write G for gravitational force. Okay, so this is Newton's second law. That's the gravitational force. Now, how do we define M here?
Total mass of the system?
Well, it is, but I mean, how do we define mass?
Kilograms.
That's not how you define mass.
Density.
How do we define mass in physics?
Density times volume?
No.
it's provided in the problem model.
There's so many ways.
It is.
No, but our official definition.
Equals MC squared, right? E divided by C squared.
No, we can bring it to that up.
M is equal to E over C squared.
I say I need to give a final in this class.
Molecules.
It's a measure of inertia,
Okay.
right? This is a measure of inertia.
Okay, so I'll give you the final.
Did anyone know that?
It's not like I didn't say it early in the semester.
Yeah.
Okay, so mass is a measure of inertia. Okay?
Since when? I'll look at
You guys remember me talking about the inertial mass?
I mean, that was a good one.
It's only 7 weeks ago. You guys, it's not been 15 weeks ago. It's a short semester.
I'm sorry, I had to cram rotational inertia into my brain.
Okay, but this mass has to do with what?
the Earth.
It has to do with the gravitational force of attraction between the objects, the amount of matter you have.
Yes.
There's nothing that says that this has to be equal to that. There's nothing that says this and this has to be the same.
So they're two separate measurements of mass?
I mean, well, the way we describe them, there's nothing that says they're
The same thing?
They're the same
both
thing.
called mass, but one of them is just saying like, oh, how much like force it would take to move the object off the path that it's already gone.
This is a resistance to as a measure of resistance to a change in motion.
And that
That's
one is
not-
its size.
Yeah. So why should be the same? There's nothing that says they're the same, and so people have done experiments to test them. And they haven't, right to 12 decimal places, I think, or 11 or 12 decimal places, they haven't been able to find a difference. So they're essentially the same thing. You can do an experiment with the pendulum, for example, or some version of that. You can write the equation of motions for the pendulum, treating the M and MA differently from the M and the gravitational force. And you'll get a ratio of masses, and that ratio is 1 to 12 decimal places, I think. And so, for now, we say that they are the same, based on an experiment, because we haven't been able to find a difference between them. I just want to say one more thing about gravity. Is there really physically, if you're in a weightless situation, or you experience weightlessness, let's say you're orbiting the Earth at the right speed and you're weightless, is there really a difference between that and being in a gravity-free environment?
Yeah.
I mean, the situations are different, but physically they're not. And that bothered Einstein. And he said, why do they have to be different? He always felt that they were the same. And so this was an important problem he thought of for years. In 1905, he came up with the theory of special relativity. It had no gravity involved. 1914, he included gravity in it. And he said that one of his principles was that you can't tell the difference between gravity-free, an accelerated frame that's gravity-free, and you being in the gravitational field. In other words, if I'm in an elevator,
In space.
yeah, and let's say in space, because there can't be any gravity around me, and the elevator is going up at 9.8 meters per second squared, and I drop the object,
Relative to the elevator?
But it's accelerating up. not-
yeah, you're in the elevator. The elevator is accelerating upward. You drop the object, let's say. Okay? That's going to be no different than you being on Earth and dropping an object. You can't do an experiment that can distinguish between the two.
I guess that's true.
And that was one of his postulates of relativity. The other one, it was that the laws of physics are the same in any reference frame. The theory of special relativity said that the laws of physics are the same in all inertial frames. He changed it that the laws of physics are the same in every frame. Now I got to be careful with that. Really, what it is the form of the equation is the same in all reference frames. But you do have to modify some of the equations, some of the laws of physics, so that they are correct. Like F equals ma is not really correct. It's correct in classical physics, but not in relativity, for example. Okay. Don't worry, you probably won't need to learn that unless you're a physics major. So I want to introduce another concept that's very useful. Actually, it's more useful in 210 but it's useful here, but it's also useful in 210. I want to talk about the concept of the field. Okay. Just 1 second. Just seemed like I skipped a note in my PowerPoint. I want to talk about the field concept. And what is a field concept? Well, you take the gravitational force and divide it by a mass. So let's pretend you're on the Earth. And the gravitational force of attraction between you and the Earth is going to be your mass, the Earth's mass, and of course, since you're on the surface of the Earth, it's the radius of the Earth. If you divide both sides of the equation by your mass, because you're small compared to the Earth, right? If you divide both sides of the equation by your mass, you get this thing. You get this thing that looks like this.
What happened with radius? Isn't the radius of the Earth plus the radius of
The
us?
person, how far you are? Yeah, it is. You're right about that. So your center of mass is about 1.5 meters off the ground. The radius of the Earth is over 6 million meters. Is it going to make a difference?
No, but mathematically, it's going to be accurate, right?
Mathematically, but there's also some you have to be practical too. Can you measure that? The answer is no. Okay, so yeah, mathematically it's correct, but in physics we have to be practical too. Okay, That you gotta take that into account. So I'm ignoring that the location of your center of mass.
Does it make a big difference if you're like on top of Mount Everest versus sea level? Is that like relatively, does that matter? Not much?
Not that much. I think you'd have to be, it'll probably change the second or third decimal place.
Okay.
Probably closer to the third decimal place. You know, when you start getting to like 100 kilometers above the earth, then you start seeing a more noticeable change.
100 kilometers?
Yeah,
That's like.
that's 100,000 meters compared to 6 million. So that becomes more noticeable.
Okay.
Okay. It depends on what level you want to see the change, right? If you're on Mount Everest, you'll probably see it at the, and I can't do the math in my head, but you'll probably see it at this, either the second or third decimal place. I don't remember. Okay. But at 1 meter above the ground, you're not going to notice that. It's going to be small. Okay. So, what do we call this?
Gravitation force of.
It's a gravitational force per unit mass, right?
Yeah.
What else have we called it?
There's G.
Yeah, this is G. Right, this is our G. And that's called the gravitational field strength. The gravitational field, the field is defined as this divided by the mass. Okay? The gravitational field is G divided by the mass. And so your gravitational field looks like that equation up there. Okay? Is G the mass of the object over r squared. So if we wrote it as a vector, okay, that's what the G is. What does this G tell you? All right. Well, in order to calculate this first, I have to realize that this is the gravitational force over a mass. This mass is called a test mass. It's small. It's small enough so it doesn't affect the field produced by the object, which here we're focusing on the Earth. Okay. That's what our G is. Basically, it says if I put an object near the Earth, it tells me if I put an object near the Earth, how big of a force it would experience. If I put a unit mass near the Earth, it would tell me how big of a force that unit mass would experience. That's what that's for. Okay. And so we define this thing called the field. Actually, you're going to see this also in 210, where you're going to divide by the force by the charge, and it'll be called the electric field.
Would that G, that is the magnitude of Fg over m, would that be the magnitude of G?
Yeah, thank you. So if you write it as a vector, then you get it right like this. And when you do this calculation, this mass has to be small. This is called a test mass. And it's going to be small because we don't want this mass to affect the gravitational field. What is a field?
Typically when I think of a field, I think of like a radius that expands over a distance in which certain things are affected. But in this case, this would be anywhere in the universe, right? It doesn't really matter where something is. There's always going to be there's going to be a distance vector that you can draw from it, right?
There'd be a field, because the gravitational force depends on one of our squares, infinite and extent. Yeah.
Isn't it just like a bunch, is it like just vectors that are pointing towards something that you can pass through?
Yeah, and that's what I'm going to draw next. I kind of skipped them, but I'm going to go back and talk about that.
Earlier you mentioned that this equation only works for objects of small mass, right? Of not great distance. And
Well, the way I calculate it is ratio. Yeah.
yeah. How do scientists actually in the real world calculate between planets gravitational force? Because if they said it doesn't work with the masses that are close together, what about the
Well, I was talking about Newton's third law, right?
Yeah.
But you can calculate the gravitational forces or gravitational fields, and I'm going to do that for continuous mass distributions, our last lecture. Okay. For point particles, it's easy, and I'll do one. In fact, I'm going to just lecture until I do the example on the field, and that's it. Okay, and then I'll stop, and then I'll talk about potential energy on Monday. Okay. So what is this field? The way I see it, it's a disturbance. So if I take a mass and put it in space, I've disturbed the mass. I've disturbed the space. Why? Because if I take another mass and put it in here, what is it going to experience?
Gravitational field.
Yeah, it's also going to experience a force, right? Okay. So I see the field idea as, you put an object in space, it creates a disturbance in space because it's change your space. Because when you put an object in the vicinity of that other object, it's going to experience a force. So you can think of it as something that creates a disturbance. Okay. Another thing is you can use the field concept to, instead of talking about the effect of a whole bunch of different particles, you can just think of the effect due to a field. Because when you collectively add all the fields together of a system of particles, you can just think of it as one big field. Because the electric field obeys the the gravitational field obeys the principle of superposition, meaning you can add them, just like forces. The other thing about the field is this: fields carry energy. You already know that. We already talked about potential energy. Fields store energy, right? Depending on height. Yeah, it's more than that. You'll see where that. And I'm going to show you where that comes from. Okay, I'm going to show you where that H comes from.
Is it now an R vector?
I'm sorry.
Is it now an R?
What do you mean? Say
The
that?
H vector.
The H, instead of it being a height, you're
It'll be an R. It'll be the magnitude of R. But then I'm going to show you where the H comes from. Okay. So they carry energy. Now, one thing I said earlier, the question was brought up about Newton's third law. When the objects are real far away, Newton's third law, you can tell it doesn't work. So that means, because the example I said is if a planet explodes, the dp/dt of the planet is not going to be the same as the dp/dt of the Earth. Where's that missing momentum?
put into the field.
It's put into the field. The field carries that missing momentum. And so that reconciles the problem with Newton's third law. The field concept is very important, and you're going to see it in 210, and when you take an advanced course in physics, you only talk about fields. So let's talk about the fields. Like you were saying, we're going to draw a source of a field. Question?
Yeah, I'm kind of mixed up. What's the difference between inertia and momentum?
Inertia is a resistance to a change in motion. Momentum is m times v. It's just a quantity associated with the motion of an object. I don't think you like what I just said.
Mulling it over.
Okay. But really, it's the difference, right? I mean, they are related to each other. But one quantity is just tells you that it's a measure of inertia. I'm sorry, let me rephrase that. Inertia is just a resistance to a change in the state of motion. MV is just momentum, mass times velocity. It's a quantity associated with the motion of an object. So you can have two objects that have the same inertia but different momentum because they're moving at different speeds. Okay. This is going to create a field in space. I can go around and then calculate the field here and assign a vector there. I can assign a unique vector everywhere in space, right, to find the field. How do I do that? I use this equation. I use a different color. I can use this equation.
Are we going to be integrating this? Because we're just doing point particles right now.
For now.
Okay.
If we wanted to do for 3-dimensional, we would have to do a triple integral to find the x, y, z right field.
For an extended object, not for a point particle.
Okay, yeah.
This is three. I mean, that's the R vector is three-dimensional.
Okay.
Okay. So anyway, let's go through, and I can assign a vector here, here, here. The vector, its length and direction are determined by that. And I can go all the way around and do this. There's a whole bunch of them. And these all look like in a line, right? I can actually connect them. When I connect these are called field lines, or in math they call them slope fields.
Yeah.
Okay. So, and the reason why this is a field, so you can define a unique vector everywhere in space that represents the field due to this object. I can connect these guys with a line to smooth them out. I can do it everywhere in space.
Could you technically say that's one vector now? Could you connect them all?
Well, this is just called a field line. So if you wanted to know the direction of the field at this point, you just draw a line tangent to it. Okay? So the actual electric field is tangent to the field line at any point. So why am I doing this? Because it's really abstract. But what if I didn't know math? I can actually use this to help me understand a little bit of what the field is. Okay. And there's going to be a lot more said about this in 210 because to me it's more useful in 210. But what are some things we know we see about this? Yeah, they point to that one spot because that's the source of the field. For gravity, the field lines always point toward the source. What happens when you're out here? What happens to how far apart the lines are?
Using the cube root law, there's
Square root.
square root.
But what happens to how far they're spread out?
It's less.
Farther and farther out.
They get further and further out. So the number of lines per unit area, so if I were to draw a sphere around this, let's say draw an imaginary sphere around this around this mass, what you'll notice is that the number of lines per unit area
It's smaller.
gets smaller.
The farther away you go.
Yeah. The number of lines going through that sphere is the same, but the number of lines per unit area going through this decreases.
And so the less lines, the less force you feel.
The less field.
Field.
The less lines per unit area, the less fields. That's what Faraday noticed. Okay? Michael Faraday noticed that.
So this is where we can connect to saying that the farther we are away from an object, the less gravitational field and force there is between, the less gravitational attraction between each object is.
Yes. This is a way to picture what a field is. These are called field lines. And Michael Faraday used this. Michael Faraday wasn't wasn't the best in math, and so he wanted a way to picture the idea of the fields. But he used it for electric fields and magnetic fields. But it works equally well here. So I draw this imaginary, I guess in 3 dimensions, it'd be a sphere. The number of lines penetrating per unit area perpendicularly through the surface decreases as you go further out. Okay? And that's indicative of the strength of the gravitational field. The closer you get, if I draw another circle or sphere, the density of lines going through this surface is the same. But now the total number of lines going through each one is the same. And you can derive an equation that relates that where you actually calculate the total number of lines going through the surface. And you'll see it's related to what's inside. You'll learn that in 210. I won't do it here.
Are the vector fields all pointing towards the center of mass? Or
Towards the source, not towards the center mass of the source. And for this guy, yeah. For a spherical one, yeah, towards the center mass, but not. But if you have something cylindrical, if you have a weird shaped object, it doesn't. I guess things with symmetry, it would point to the center mass. If you have a line or a cylinder, it would point towards the axis of the cylinder. So these are the field lines that Faraday used to try to understand better what a field is. Okay. So we say a little bit about fields here. When you take 210, you're going to learn a lot about more. Now, this field idea is abstract and sometimes confusing, but it can make difficult problems easier to solve, and that's what it's hard for the students to grasp. Okay. The idea of the field can make difficult problems easier to solve, even though it might not look like that right now. Okay. Because there's some relationship you can develop that'll make life easier for you. Okay. So what I want to do is look at this example. I want to find a location where the field in space is 0. And then I'll stop here. Okay, so big mass, little mass, there's separation. There's 1 meter. First of all, I got to ask the question, where's the field going to be 0? I mean, what area do I have to consider? I mean, is the field going to be 0 over here?
No, in between them.
Why in between them?
Kind of like if you think of the idea of tension, like one of them is going to be pulling, like one way, and the other one has to be pulling the other way.
Yeah, the field always points towards the source, right? The gravitational field always points towards the source. So if you're somewhere in between here,
You're going to even out something.
yeah, you have one this way and one this way. If you're over here, they both point that way. If you're on the other side, they both point that way. Okay, but if you're in between, they both point opposite direction. It becomes a little more complicated when you do electric fields because when you have a positive and negative charge, it changes things a little bit. Okay, but for this problem, it's going to be somewhere in between. Okay, so let's call this distance. What do you want to call this distance?
D.
D. Okay, so we got to solve for D. So I want the field due to this mass to be equal to the magnitude of this field to be equal to the magnitude of that field, right? The magnitude of this field is big G times 9m over d squared, right? Really what I have to do is sum the fields and set them equal to 0, right?
Would it be negative?
Okay, yes, you're right, it's negative. Okay. And what about the field? The other fields will be positive then, right?
Mhm.
What do I put in the denominator?
1 minus d squared.
What is it?
1 minus d squared.
Oh, good, good. How did you know that? How did you know to write that?
Because the distance between them is 1, and if you put in another variable for that point for the center of mass of 4m, you'll have one equation for 2 unknowns.
You don't want that. You know that the total distance is 1. You know this distance, so then distance has to be 1 minus d. Okay. So, even though it's a simple problem, there's something to consider when we solve this. Can I cancel things, by the way? I'm going to erase this.
Yes. You can cancel the big G's and the masses.
Okay. So let's do that. Actually, I'm going to write in black again because it's easier to see. It's not black.
Easy to see.
Of course, I can move this to the other side of the equation, right? Get rid of the minus sign. I'm going to cheat. I'm going to do this. Question?
Is your 1D under the 4 squared
Yeah,
still?
it is.
Yeah.
Thank you. How would you solve this now?
Cross multiplication.
Yeah, multiplication.
You want to cross multiply? Okay, let's do that. Let's cross multiply. So this times this, so 9. Then what?
Did you read it?
If you want to FOIL this out and do all that fun stuff, right?
I feel like there's gonna be like some easy trick there.
Just write it all out.
Just write the whole thing out, right?
Right,
that's
and then
the
put all the
ninth
d's on
algebra.
the side.
And you got to use the quadratic formula then, right?
No, we don't. No, we don't.
Why?
It's squared.
You what? Say that again?
We don't,
Why?
because,
Gravity.
well,
we do.
No, go ahead. What were you saying?
because we multiply, we factor in the 9, we only put 9 minus 9d, oh, yeah, you're right.
It's squared though, right?
That's the way the,
No, I thought you were saying something correct.
I made a piece of mistake.
What's a trick I can use to solve this right away?
You just square root both sides.
Yeah, take the square root of both sides.
Oh, man, of course.
What if I take the square root of both sides?
Oh,
You
man.
can't do that.
Oh, man. I forgot about that.
Is that a little bit easier?
Thank you, yes.
with their math.
Humans.
Okay, and that's your answer. It's got to be closer to the 4m, right? Because the 4m is lighter. The reason why I like going through this is because I used to do this as a student too. I've done that as a student, and then you think, like, take the square root. It's way easier,
It's,
right? Well, you'll find if you use the quadratic formula, one of the solutions is not going to work. Okay. Yeah, you'll get a negative answer. So, okay, so I'm going to stop here. I went further than I had wanted to. So on Monday, I'm going to introduce the concept of potential energy, and then I'll show you where MGH comes from.
Wait, so to get like the value of the whole field, we would just integrate all the points, basically?